All right, let's just go through these answers. If I could have everyone's attention. Okay, so I think the hardest one for most of you, or the hardest stuff for most of you, was balancing equations and like definitions. So remember, a polar compound, or the most common polar compound, is going to be water, and a polar compound has electrons. Are you guys paying attention?
I got that first one right.
Yeah, probably. I don't remember. I haven't gone through every single answer yet. So a polar compound has electrons that are slightly pulled to one side of it. So there are going to be partial charges. So there's going to be like a slight positive on one side and a slight negative on the other, because the electron's being pulled kind of more towards one side of the compound, but not fully all the way. It's not ionic, a little different. Okay. And then a nonpolar compound, they're sharing electrons in a covalent bond, and the charge is distributed throughout the compound. Okay. Now with these questions, super easy. You just have to remember like dissolves like. So if you have a solute, that's what this is, the solute, that's polar, you would need a polar solvent to dissolve it. So the answer should match this word, because it has to do with like the charges actually pull apart the molecule when it's polar.
Probably would have got one question wrong on that.
So this one's polar. This solute is nonpolar, so it needs a nonpolar solvent. This one's polar, so it needs a polar solvent, so likely water, right? I'm going through the answer key. You can just pay attention. You don't have to take notes. Yeah, if y'all want to take notes or anything, I'm recording this, so because there are a few people out for testing today. But if you want to take notes, you can as well. Okay, so remember ionic compounds. So when we're making ions, one electron is stolen from another atom to make that compound. So say we're making a salt. We have a halogen, which has 7 valence electrons. And then we have something from group 1, the alkali metals, that has 1 valence electron. Well, the alkali metal wants to get, like, if it's lithium, wants to get rid of its 1 valence electron. So the halogen will steal it, and it will become a negatively charged ion, or an anion. And then that makes the alkali metal, the one from group 1, positively charged because it got rid of that negatively charged electron. So that makes it a cation. Then those things have opposing charges, and what do we know about opposing charges? They're attracted to each other. So an ionic compound has a fully separate charges in the compound. So kind of like polar, but like more charge, more of a difference between the charges, instead of polar where it's a partial charge. But we're thinking about those charges, those opposite charges, and if the solvent is polar, it does have that partial positive or negative charge, and that is able to dissolve an ionic compound. So if you see ionic, it dissolves in polar solvents. Okay. So polar dissolves in polar here, polar dissolves in polar, ionic dissolves in polar, nonpolar dissolves in nonpolar. Okay. Solute. So solute is the thing that is dissolved in the solvent to make a solution. It's usually the smaller part of the solution. We're what else can I say about it? Usually it's a solid. Sometimes it can be a gas. And then solvent is
Acid.
something like water. It's what's actually dissolving the substance to make the solution. So it's going to be the majority of the solution. So if I have, you know, my coffee and I'm putting sugar in it, coffee is the solvent, is the majority, and the solute is the sugar that I'm dissolving in it. Dissolving salt in water increases the conductivity of the solution, making the solution a strong electrolyte. So remember, so salt is an ionic compound. Like I said, it's got something from group 1 and a halogen from 17. So we have those kind of, that electron movement. So when we dissolve it, we have those charges able to move around, and we can conduct electricity with the solution. An electrolyte is basically like a solution with like electrons that can become a conductor. To dissolve more solute in a solution, you could increase the temperature. So you're not going to decrease the amount of solvent. That's not going to help you dissolve anymore, right? Remember, when we're looking at our graphs, it's a very specific amount of solvent. If we decrease the amount of solvent, we also have to decrease the amount of solute, because there's only a certain amount of solubility, and that ratio is going to stay the same. So you basically, the only thing you can do is increase the temperature. If you decrease the temperature, you're going to decrease, remember, this is grams of solute. So as the temperature goes down, the amount of solute that can dissolve will actually be decreasing most of the time. You could increase the amount of solute, yes, but it's not going to go, the amount that actually dissolves is not going to go above the solubility line unless we increase the temperature. So if I'm at 40 degrees, I can only do this 105 grams right here. If I put in more, I'll just have more, it'd be like up here. But unless I actually increase the temperature first, I wouldn't be able to dissolve that into the solution. So increasing the temperature. All right, the difference between saturated, unsaturated, and supersaturated. Saturated has the maximum amount of solute. So I'll look at like, I guess I'll go back to this line. So saturated is the line. That is where saturation occurs. That is the maximum amount of solute. Now, unsaturated is going to be, there's less than the amount. So anything underneath the solubility curve is unsaturated. It's less in the amount. So I could have it at, you know, whatever temperature. If I only put in 70 grams of solute instead of going all the way up to the point of saturation, which you can do, you know, then I'll just have 70 grams of solute in there. That'll be unsaturated. And then supersaturated, remember we have to increase the temperature to reach whatever the point of saturation is for that amount of solute we want in there. And then we have to decrease the temperature, and it keeps the amount of solute in the solution. So say I'm here, 10 degrees Celsius can dissolve 80 grams of solute in the solution. And I decide I want to do 100. Well, I'd have to increase the temperature to 35 degrees Celsius from 10 degrees Celsius to get that 100 grams in there. And then I could cool the temperature back down and it would stay in there. So anything above the line is supersaturated. Okay, now graphs. Now remember to kind of read and look carefully when you see any visuals, especially when we're doing the final. How much KNO3 will dissolve in 100 grams of 50 degrees Celsius water? Okay, so the 100 grams of water is already there. Don't have to worry about that. That applies to the whole graph. 50 degrees Celsius, and we're looking at KNO3. So 50 degrees, and I'm gonna run up from that point. And then we have 80 grams. So just hit the temperature and go all the way up to the solubility curve for whichever solute you're looking at. And that'll be 80 grams. 70 degrees Celsius, NH4Cl. Did I say 70 degrees? Okay, so 70 degrees. Go up until I hit NH4Cl, and it looks like the answer is 60. Which substance is the most soluble in 100 grams of water? Okay. So looking at this graph, I mean, this one's pretty easy because the solubility at 0 degrees for Ki is like way up here. So I'm going to say this is the most soluble. Which substance is the least soluble? So the reason that it's NaCl is because this line is so flat. There's not really a change in slope, and that's what makes the difference here. Instead of just picking the one that has, you know, the furthest at 0, or maybe the one that's going negative. Plus, out of your choices, you have this one, which does reach a higher solubility. What else? You have Ki, which is the one we said was the most soluble. It's way up here. And you have NH4Cl. Yeah, I already said that one. And KCl. So these are above that. Out of your answer choices, this one has like almost no slope. It's pretty much can only hold up to 40 grams at any temperature. Okay, if you dissolved 100 grams, okay, 100 grams, 10 degrees Celsius water. Okay, so we're looking at 100 grams. So right here in 10 degrees Celsius water, which is this first thing, and we're looking at Ki right here. So since we're underneath the line, it's unsaturated. If you dissolved 80 grams, NaO3, 80, NaO3, there's the solubility point at 10 degrees. So I'm at 10 degrees and I'm at 80 grams and we're right on the line. So that's saturated. If it was up here, it'd be super saturated. If it was down here, it'd be unsaturated because we're looking at this line right here. Why does it look like that? Man, there's so many graph pictures. Okay, 50 grams of KCl in 80 degrees Celsius water, then lower the temperature. Okay, so let's start with the first part. 50 degrees, or 50 grams, sorry. KCl, so we're right here in 80 degree water. So we're at the point of solubility right there. Then lower the temperature to 40 degrees Celsius. So we're at the point of solubility. And then we're lowering the temperature, so we're going this way. So now our point is right here. So we're above the line. So we're super saturated. Okay, define an acid. Acids donate protons, which are hydrogen atoms. They're sour and corrosive. You can think of like Citrus, things like that. Sodas are acidic. If you ever get acid reflux, that's very acidic. Okay, defining a base, they donate hydroxide ions, which is OH. They're slippery and bitter. You can think about, household cleaners, soap, things like that. Okay, gases. So this was in the PowerPoint, all on one slide. You guys could have found the answer at the end of the solutions PowerPoint if you didn't. Gases dissolve better at lower temperatures. Remember, think about the ocean. And we talked about the example of the ocean and how the lower the temperature is, the more gas there will be. Also think about soda. That's easy too. If you want to keep your soda carbonated, you keep it in the fridge. If it gets warm, it's gonna get flat. Gases dissolve better when they are not shaken or stirred. Remember, if you shake, a soda, all the gas is gonna come out in the form of like bubbles that go everywhere. Gases dissolve better when the pressure is increased. So pretty much kind of the opposite of what we think about with solids. Because most solids are going to dissolve in higher temperatures and be stirred. Does anyone have any questions on Unit 4? Okay, moving on. Okay, when there is a chemical change, how are new substances produced? So we are making and breaking bonds. So we're talking about like a chemical reaction. Bonds are actually like changing. Some of the atoms are moving around. Think about your chemical formula and how one atom will be in this compound, and then on the product side, it's in a different compound. Okay, when a precipitate is formed, there is no chemical reaction, no. Two solutions remain clear and unchanged, no. Remember, precipitate was one of the indicators of a chemical change. So, and it was like a solid. It was like that cloudy kind of look. So it was like two clear liquids would mix together, but the chemical reaction would actually form kind of like a cloudy colored substance. And if you let it sit long enough, it would the dust would settle and the solid would fall to the bottom. Which of the following are indicators of energy transfer? Production of light, production of sound, change in temperature. So remember, energy transfer is like a big part of chemical reactions. And these are all forms of energy that are just changed forms. And they're also indicators of chemical reaction. Light, sound, and change in temperature, all indicators of energy transfer and chemical reaction. 3 examples of chemical change. Remember, we had that like slideshow of like 8 pictures that we like picked out, which were physical and which were chemical changes. Some of y'all found some good examples. A lot of people put baking and cake. So I'm assuming that's like the first thing that pops up on Google. My examples that I put would be like baking soda and vinegar. So, you're making a homemade volcano. That's a interesting reaction to watch. Rusting, cooking, glow sticks. Those 3 were all on the PowerPoint. Which subatomic particle is involved in the formation of bonds? Valence electrons. Remember, it's all about the valence electrons. That's what explains all the bonding we've talked about and all of the characteristics we've talked about this semester. Written after a symbol to tell how many atoms of that element are in a unit of the compound. That is a subscript. After the symbol would be your keywords there. A short or abbreviated way to write the name of an element, chemical symbol. Are you checking your answers or are you changing your answers? Okay. All right, SLG and AQ represent the state of matter. Remember, S is solid, L is liquid, G is gas, and A is aqueous. Shorthand method that uses symbols to tell what elements are in a compound and their ratios. That is chemical equation. The number of units of each substance taking part in a reaction, that is coefficient. So the difference between coefficient and subscript is that subscript is specific to the atom it is after, unless it's outside of parentheses. Whereas the coefficient applies to the entire compound. So any atom in that compound, the coefficient applies to. Conservation of mass, most of you got that. Mass cannot be created or destroyed, but it does change forms. Well, that's energy, it doesn't really change forms. But it does move around. Okay. I'm gonna draw these out for y'all. Let's see. Okay, so I'm going to count my atoms on each side. Remember, you want to count. Is it going to work? You want to count the reactant side and the product side like as wholes. Don't be counting each individual compound. So I have 1 over here, 1 over here, I have 1 hydrogen over here, 2 over here, I have 1 chlorine over here, and 2 over here. So the first thing I notice is that I have 2 hydrogens and 2 chlorines on the product side and only 1 on the reactant side. And if you notice right here, they are together. So all I have to do is put a 2 here. And then that makes this even. So that's why I put 1, 2, 1, 1 as my answer. Okay. Next. Now this one looks complicated, and it kind of is. But we got this. Okay. So L C H O. Okay, so I got the subscript 4 right there. So I have 4 on this side. I don't have anything here. I just have this 1. Okay, I have this subscript there. So I have 3 carbons on this side. Looks like I just have 1 carbon on this side. Remember, this subscript right here by the hydrogen only applies to the hydrogen. However, this one right here applies to the O and the H that are in here because it's outside of a parentheses. Okay, so let's see, hydrogens, I have 2 on this side, and I have 1 oxygen on this side. And then let's see, hydrogens, I've got 4 from this first one, and then I have this 3 subscript applies to this hydrogen, so that's going to give me 7. And then oxygens, this 3 applies to the oxygen as well, so that gives me 3. Okay, let's see. What do I think about? Okay, I know I need 3 carbons on the product side to match this 3 carbons over here. So I'm going to try that 3 there. And I'm also going to try this 4 because I know I need 4 aluminums to match this 4 on the reactant side. So I'm going to go through and recount. So this 4 coefficient applies there. So that gives me 4. This 3 coefficient applies to the carbon. That gives me 3. Now hydrogen, I have to be careful because I have 2 different places that the hydrogen's in. So I need to make sure that I'm doing my due diligence to double check that. So 3 times 4 is 12. So I have 12 from right here. And then 4 times 3, another 12. So I'm going to be at 24. And then let's see, my oxygens, looks like I have 12 oxygens. And then now you can see that these are, what is it called, factors? I don't remember math terms. I don't know. You can do 24 by 2. And we have this 2 coefficient here, or subscript here on this hydrogen, on this water molecule. So all I have to do is put a 12 here, and I'm good to go. That gives me 24 and 12. All right. So again, you want to CHO, make sure you're counting carefully. I've got 1 carbon on this side, 1 carbon on that side, 4 hydrogens over here, 2 over here. I got 2 oxygens and 3 oxygens. So I should be able to make these both equal 6. It's kind of my thought, is when I first look at this. So did I write the answer wrong on here? No, okay. Actually, I don't even need to do that. That's not right. Okay, so let's see. Okay, so I know I'm going to need to put 2 here because I have 4 hydrogens on the react side. So now I have 4 hydrogens on the product side. And then if I re-add my oxygens, I've got 2 from there and 2 from here. So that gives me 4. My carbons are good, so I don't need to mess with that. And then now I just have to deal with this. So I put a 2 there. And then I'll change that to 4. Okay, last 2, and we're done. Okay, this one, I can almost do in my head, but let's see. We've got iron, and we've got oxygen. Okay, I got 1 on this side, 2 of that, 2 of this, 3 of that. So, yeah, this is the case in where I'm going to make both of the 6, since they can multiply each other. So I'm going to put a 2 there and a 3 here. And that's going to make that 6. That's going to make that 6. And then 2 times the 2 subscript is going to be 4. So I know I need a 4 over here to even it out. Okay, oxygen. I got 1 and 2, 1 and 1. So I know I need to put a 2 here to equal out the oxygens, and that's also going to give me 2 on this side. So I need a 2 right there. Boom. And so that would make that a 1. Okay. I know I went through, wait, what do you do with 6? Do you just leave them? Which are you talking about? Sorry, I just saw that. Are you talking about right here?
Yeah, so do you just leave the 6 like I'm confused.
They have to be equal on both sides. So I'm doing my count. I have 1 and 2 and 2 and 3. And the reason why I'm making them both equal 6 is just because it's the easiest way to do it. So like 3 times 2 and then 2 times 3.
Okay.
So
Okay. I think
that's
I
why,
understand.
like, when you just look at stuff that's unequal like this, usually they can multiply by each other and they'll even out. Does that make sense?
Okay. Yeah. Okay.
Okay. So I know I went through that kind of fast. Like I said, I'm recording this. I'm going to post it on the classroom so you guys can rewatch. And then I also posted like at least 4 videos on balancing equations. So hopefully you guys have looked over that. Does anybody have any more questions on balancing equations before I move on? Okay. All right. Okay, so we're doing conservation of mass. So remember, conservation of mass is basically just solving for x. So, so we're adding, what's going on? Can you work properly, please? So we're just adding this and this together on the reactant side, and it has to equal this plus this. So if you make this your x, you subtract the 152 from this side, then you're going to end up with 40 grams. Is that right? I'm doing that. That's not right. I think it's 104. Yeah, 104. Sorry. I must have clicked the wrong thing. Yes, no. There we go. Okay. So you're going to end up with 104. So remember that when we're talking about conservation of mass, mass cannot be created or destroyed. So that's why all of the weights of these have to end up equaling. So this side needs to be equal to this side. So it's just a quick equation. Just seems more complicated than it is. Okay. Now you want to look at this. Illustration shows a conservation of mass experiment. The solution in the beaker lost mass because, okay. So we can see heat. See 100 grams. So the 100 grams is now heavier. So that means that this has lost weight. If you look at the equation, we're creating water. That means this is a combustion reaction. Sodium sulfate is lighter than air. The mass of the reactants in the product is less than 100 grams. Materials have less mass at high temperatures. Okay. Materials have less mass at high temperatures. No, not true. Mass doesn't change. Remember that. the mass of the reactants and products was less than 100 grams. If we actually go up and look at this, this is a balance basically, and it's even with 100 grams, so that's not true. Sodium sulfate is lower than air. Well, we have sodium sulfate in this as an aqueous solution right here, so we know that's not true. So some of the water molecules turn into gas that got released with the heat. The chemical equation shows CaCO3 being heated. Which of these statements best describes the mass of the products if 100 grams of it was heated? The sum of the product's masses equals the mass of the reactant. So remember, both sides of the equation, not only do the equations themselves need to be balanced, like the chemical equations need to be balanced, but the masses also need to be balanced. The mass of a rusty bicycle is found to be slightly greater than the mass of the same bicycle before it was rusted. The change in mass indicates that the rusting process is a physical change. No, we already know rusting is a chemical change. Involves an energy to matter conversion. No, decreases the density of the metal. If it decreases the density of the metal, it wouldn't be heavier. So metal bonding with other atoms for outside is how you get a change in mass, because we actually have the reactant side, we're going to have like our bicycle metal, right? And also our oxygen that is going to oxidate the metal. So on this side, you have the oxygen actually bonded to the metal, and that's going to increase your mass. Okay, so just basically another conservation of mass, but it's in a different format. So always read carefully. Okay, copper and sulfur were heated in a covered container. After the reaction was complete, the unreacted sulfur was removed. The table contains the results of the investigation. Okay, so if I am drawing this out, of copper and 2.93 grams of sulfur. So this is my reactant side. So I know it's really messy, I'm sorry. And then we get 4.78 sulfur plus X grams of unreacted sulfur. So you're basically solving for X again. So this reactant side needs to equal the product side. So if you subtract the 4.78 over, you're going to get 1.32. So just another way of, long form, making an equation. Okay, so this one is kind of, balancing equations, basically. So you want to look at your reactant side, what you have. You have carbon, hydrogen, and oxygen. Okay. Actually, I'll go ahead and draw them. So I have carbon, hydrogen, and oxygen. On the product side, I have that's 4. Always count your subscripts. I know they don't look like subscripts because of the formatting, but 4 hydrogens and 10 oxygens. And so right now I have 4 carbons and 8 oxygens and 0 hydrogens. So I know I need 4 hydrogens and 2 oxygens to balance this equation. So remember that coefficients apply to both things. So, and subscripts only apply to the one, the atom they're attached to. So this is gonna give me, this one will give me 4 hydrogens and 2 oxygens, which is exactly what I need. And then, let's see, this is giving me carbons. I don't need more carbons. This only gives me 2 hydrogens. That's not enough. This one gives me 4 oxygen. That's too many. So first answer choice. Let's see. I think almost done. Okay, so calcium chloride, sulfate solution to create the product shown, which of the following is illustrated by this activity. So this is literally just conservation of mass. So even though things are reacting, the mass is staying the same. So it's conservation. And then which side of the equation shows the reactants? That's going to be the left side of the yield arrow. And the side of the equation that shows the products is the right side of the yield arrow. So that's the whole review. I'm going to try to post it. I'm having issues.